Hello, my name is Hernando Burgos, a mathematics professor, and today I will be speaking about the basics of probability theory. Consider an experiment of rolling a six-sided die. What is the probability of obtaining number 4? So I am asking you about the probability that when the die finally lands, the number that is at the top is number 4. So there you see a face like this. And the question is in this way, the probability of that happens. You have here that this is 1 over 6. Today I will be explaining why is 1 over 6 and also why this is not always true. Before doing that, I will be explaining some basic concepts of probability theory. One of these concepts is the concept of experiment. Look at in the question I say, consider an experiment. What is an experiment from the point of view of probability theory? So an experiment will be any set of actions that can produce different outcomes. Any activity that produces different outcomes is an experiment. When the process is carried out, it always finishes with the observation of one of the possible outcomes. So this observation, what we observe, will be very important in this process, in the experiment. So an experiment with different observation, even if the set of actions are the same, but the final observation is different, will be a different experiment. For example, here, the experiment consists of rolling a six-sided die. I can observe what is the number at the top when the die finally lands. But we can also observe or pay attention if the die is going to land on the desk or on the floor. Look at that. The first experiment had 6 possible outcomes because we are observing the face at the top. But the second experiment that have the same set of actions is different because it has just two different outcomes on the desk or on the floor. So an experiment is well defined when you have defined what is the observation that you are going to do at the end of this experiment. So that define these observations are going to define the possible outcomes. This experiment is also called a random experiment when you are speaking about probability. Another important concept in probability theory is the concept of sample space. And the sample space will be the set of all possible outcomes of the random experiment. For example, when you are rolling a die, the experiment produce or can produce 6 different outcomes. So for that reason, if the observation is observing what is the number at the top. So for that reason, this experiment have these possible outcomes and this sample space. So from 1 to 6 have 6 different outcomes. If you get a subset of this sample space, you get to the concept of event. An event is any subset of this sample space. And an event is what I'm going to use to ask you what is the probability of this event. So an event is this something that I'm going to use to ask you what is the probability. So when I say what is the probability of these things that are coming in the question is an event. So this is an event because this is a subset of this sample space. But actually there are many others different events from this sample space. So it will be a good idea to ask ourselves how many events in a sample space. If the sample space S has n possible outcomes, then the number of possible events is 2 to the power n. For example, if we have this sample space that have three elements, A, B, C, let's say that the experiment was choosing randomly the three first letters of our alphabet, and this is the sample space. You can choose A, B, or C. How many possible events? So because they say that the number of possible events are 2 to the power n, so I'm sure that the number of events will be 2 to the power 3, because we have here three elements in these three possible outcomes. There are three outcomes in the sample space. Then the number of events in this from this sample space will be 2 to the power 3. And this is 2 to the power 3 is 8 for sure. 2 to the power 3 equal 8. What are these events? Let's see if this is true, that we have actually 8. The first event, we have, this is the sample space ABC. The first event that I see is the same ABC. So for example, if the experiment was choosing the one of the three first letters of the alphabet, one possible event, one possible question will be, what is the probability that you obtain one of these three letters? So the same sample space is an event. So I can ask you, what is the probability of choosing one of these three letters? So these three letters is one event. So the same sample space is always an event. And this event is very important. It's called the shear event. So always the sample space will be an event. Let's see other possible events. Maybe there is an event that has two possible outcomes. For example, A, B. This is another event. So any subset, remember, any subset of a sample space is an event. So AB will be another event. AC another event. BC another event. So it will be some events here that have two elements. Another possible event, another possible subset will be A that have only one element, for example, 8 or just B or just C. If you count, so these are the events that have three possible outcomes. There are events that have two possible outcomes. There are events that have one outcomes. If you count this 1, 2, 3, 4, 5, 6, and 7. So far we have 7 events from this sample space. And these events that have only one outcome, is what we call elementary events. So we have elementary events, and these are the events that have only one possible outcome. But I told you that there were eight possible events. There are 8 events from a sample space that have 3 events. The reason is because 2 to the power 3 is 8. What is the other one? Because we have here so far 7 only. The other one is one that is coming from the empty set. So the empty set, when we don't have any elements, is also always an event of any sample space. And this is always will be an event, and it's called the impossible event. So this impossible event is the one that doesn't have any element. The shear event will be the event that have all the elements in the sample space. Now, how can I ask you a question of a probability using this set? For example, the experiment is choosing randomly one of the 3 letters of the alphabet. What happens if I ask you, what is the probability of choosing a D? But D is not here. So D, it doesn't appear. There is no event, there is no subset that contains the letter D. So this is the empty set. Okay? And this is what is called the one impossible event. An impossible event is one that doesn't have any outcome. Let's see an example. How many events can we define from the sample space that we were speaking about some moments ago? Yeah, so the sample space coming from the experiment of rolling a six-sided die and observing what is the number at the top. Because they have 6 elements, then the number of events will be 2 to the power 6. So 2 to the power 6 will be 64. Will be a good idea if one of you try to get all of them. Yeah? For sure, one of them will be the same sample space. So one event will be the sample space, and this will be the sure event. And it will be another event that for sure it will be the empty set. That will be another event. And then the others that have one, some of them have one element, some others have 2 elements, some others have 3, some others 4, etc. Until the one that have 6. Let's learn a little more about events in a sample space. If A and B are events, then there are also other events called no A or B, and A and B. Remember that the events are these things that I can ask you what is the probability of it. So if I can ask you what is the probability of A, then I can also ask you what is the probability of no A. If I ask you the probability of A, and I also can ask you the probability of B, I can ask you what is the probability of A or B. Or I can ask you what is the probability of A and B. So these 2 events define others 4 events, because remember that will be also an event that is called no B. Yeah? So no A, no B, A or B, and A and B. Sometimes this event, no A, is symbolized in this way, with this tilde beside. Yeah? No A. Now, if we know what are the elements in A, what are the outcomes in A, we are going to know what are the outcomes in no A. So an outcome belongs to no A if doesn't belong to A. That's it. So it belongs to the sample space, but is not in A. Let's see what is A or B. A or B is also symbolized like A union B. Some people call it this way, A union B. And how I define this A or B? An outcome belongs to A or B if it belongs to A or belongs to B. So if we want to know, is this outcome in A or B? Or just check if this is in A or if this is in B. If this is in one of these two, it will be in A or B. Sometimes we say it belongs to at least one of the events. And sometimes the questions will be, what is the probability that this is at least in one of these 2 events, for example. And you see, oh, I need to compute the probability of A or B. Finally, A and B can be symbolized in this way. This symbol here is the opposite that we were using in the OR, so the union symbol. This is what is called the intersection symbols. An outcome belongs to A and B if it belongs to A and belongs to B. And of course, you can write this that it belongs to both events. So it's easy to recognize when the outcome is in A and B. It needs to be in both events, A and B. Let's see this. Let's explain this with an example. Imagine that we have the same sample space that we have at the beginning. Remember the one from the experiment of tossing a die? And now we have these 6 possible outcomes, but I'm going to choose 2 events. Let's see that the event A will be this, 2, 4, and 6. It has these 3 possible outcomes. You can say that this is an event that have all the even numbers. you can ask what is the probability of A, or you can ask in this way what is the probability of obtaining an even number. This is an event. Another event, let's say this 5 and 6. This is event describing all the possible outcomes, but also you can say it in words. What is the probability of obtaining a number that is more than 4? If you toss a die, okay, there will be this event. Yeah. So the events is actually the things to which you are going to ask the probability. The thing of which you are going to ask the probability. What is the probability of obtaining, for example, more than 4? So this is another event. What will be the event, for example, the event no 8? The no 8 will be the event that have all the outcomes that are not here. For example, 1 will be in this. So it will be 3 outcomes. Yeah. So let's open bracket and let's type all the events. For example, all the outcomes. There is one outcome, number 1 is not here. So number 1 will be a possible outcome for no A. Another possible outcome is 3 because it's not in A. Another possible outcome is 5. Yeah? So all the odd numbers, because in A we have the even numbers. This is the no A. There is another event that is called no B. No B will be all the elements that are not here, yeah? And I noted that are from 1 to 4, yeah? So no B will be 4 elements, and these elements will be number 1, number 2, number 3, and number 4. That will be no B. And what is the event A or B? A or B, to be in A or B, need to be an element that is in A, an element or an outcome is in A or B, if the outcome is in A or is in B. For example, number 2 must be here, yeah, number 2. Number 4 also must be here. Number 5 must be here. Number 6 always is here because it's here and it's here. So for sure number 5. But number 5 is also in A or B. So this will be the event A or B. And there will be an event that is called A and B. The outcome is in A and B if it belongs to both events. And there is only one outcome that belongs to both events, yeah? And this is outcome number 6. So this event have only one element, yeah? Or only one outcome, 6. So A and B have the elements in common. One way to represent the events in a sample space is using what is called a Venn diagram. An event diagram is done in this way. The sample space will be represented by a closed figure. So we can use a rectangle, for example, that represents the sample space, and any event of the sample space will be another figure inside of the sample. So you draw another figure, it could be a circle, for example. And if we are speaking about the event A, so this circle will be represented the event 8. The event no A will be everything that is outside of A. So no A will be everything outside. I can shade this outside of 8 and they say that this is no A. We can use a Venn diagram also to represent 8 or B. Again, the sample space, we draw for the sample space a rectangle, could be. And then we have two events. We can draw 2 circles inside, one for 8 and one for B. Could be an intersection between the 2 circles. That could happen. Yeah? Obviously, the 2 circles could be separated. Why not? Yeah, this is a way to represent the A or B. So we shade all the area inside of 8 and B. Yeah, both of both events. And to represent 8 and B, then again, remember that A and B are the elements that are at the same time in 8 and B. So we draw this sample space. We draw the 2 circles, from one from A and the other for B. And A and B will be the common area. So these, all the elements that are here at the same time in A and in B, represent A and B as a Venn diagram. That leads us to the concept of mutually exclusive events. There will be sometimes that this A and B doesn't exist, so that the two circles are separated. There are no common elements. And if that is happening, we are speaking about mutually exclusive events. So we call it also disjoint events. And two events are mutually exclusive if they have no outcomes in common. Yeah? So they cannot happen at the same time. For example, if you toss a die, you cannot obtain an odd number and an even number at the same time. You toss it only once. Yeah? So for example, if we have this event, tossing a die, and we have the event A, obtaining an even number, and an event, let's see, event C, obtaining, let's see, an odd number less than 4. So 1 and 3. If we have these two events, they don't have a common element, they don't have a common outcome. So in this case, we have two mutually exclusive events. And we represent the two mutually exclusive events in like two circles inside of a sample space, but these two circles don't touch each other. Now that we define this concept, we are in the position of defining the concept of probability. Then what is probability? Given a sample space S, and when I say given a sample space S, I'm saying given an experiment that produced this sample space S. A probability is a rule that assigns to each event of E, so it means each subset of the sample space, a number P of E, a number that is called probability of E, with the following properties. And it has three properties. The first property needs to be this one. The probability must be greater or equal than 0 and less or equal than 1. So the probability of an event cannot be negative or cannot be more than 1. So it will be a number that is between 0 and 1, and that will be the same property. The probability is really a probability. It is always between 0 and 1. The second property is that the probability of the sample space need to be 1. So the probability of the sure event is 1. And the probability of the empty set, so I mean the probability, remember that the empty set is another event, the probability of the empty set need to be 0. So the probability of the impossible needs to be 0. This is another property of a probability. And finally, if we have two events that are mutually exclusive, then the probability that one of these, at least one of these two happens, so the probability of A or B will be the probability of A plus the probability of B. With this condition, the two events need to be mutually exclusive. And whatever rule that has these three properties, this is a probability. So it means now that the probability can be defined in many ways. If this probability satisfies these properties, these three properties, then will be a probability. And I'm going to tell you one way to define a probability. This is what is called the classical probability approach. You can use this classical probability approach if all the outcomes in the sample space are equally likely. There is one condition. S need to be finite. So the number of outcomes in S need to be finite. If that is the case, then you can compute the probability of E equal the number of outcomes in the event. So the probability of the event will be the number of outcomes in the event divided by the total number of outcomes. People say number of favorable outcomes divided by the total number of possible outcomes. Let's see an example. Consider an experiment of rolling a six-sided die. So we continue with the same example. What is the probability of the event an odd number of spots appears face up? So what is the probability of obtaining an odd number? The sample space, as we know, will be this when we have all these six possible outcomes, and the event will be the one that have the odd numbers. Yeah, so the event will be 1, 3, and 5. So if you want to compute the probability of E, will be the number of favorable outcomes divided by the total number of possible outcomes. If you do that, so the number of elements in E is 3, the number of elements in the sample space is 6, will be 3 over 6. Or you can type 1 over 2, or just use your calculator and say this is 0.5 or 50%. So there are many ways to say, there are several ways to say, to answer this question. So you can say 1/2, or you can say 0.5, or you can say 50%. Notice that this definition follows all the properties of a probability. First, if we want to compute the probability of the sample space, it will be the sample space will have 6 elements divided by 6 that are the total outcomes. 6 divided by 6 will be 1. So this satisfies the property that is the probability of the sample space needs to be 1. The probability of the empty set, because the empty set has 0 elements, will be 0 divided by 6. It will be 0. It will be always a number between 0 and 1. And obviously, if we have two, let's see, mutually exclusive events, the probability of the A or B, will be adding together the two probability. So this definition satisfies the three properties of a probability. Let's see another example. A group of employees of unique services is to be surveyed with respect to a new pension plan. In-depth interviews are to be conducted with each employee selected in the sample. The employees are classified as follows. So there are supervisors, maintenance, production, management, and secretarial. And these are the number of employees in each of these classifications. The question is, what is the probability that the first person selected is in management? So if I add together all this, I notice that there are 2,000 employees. If I want to compute what is the probability that the selected person is from management, let's see the event, I call this event D. So I asking you the probability of D. So I need to know how many elements are in D, but this table tells you how many elements. So the number of elements in D is 302, and the total numbers in the samples is 200. So it will be then 2,000, sorry. So then the probability will be easy to compute, will be 302 divided by 2,000. Will be then the probability will be the number of the elements in the events, D, divided by the number of elements in the sample space, will be 302 divided by 2,000, and that gives me 0.151 or 15.1%. 15.1%. And that gives you what is the probability of selecting one person in management. Let's see another example. This experiment will be rolling two six-sided dice. So it's different than the previous one. It was selecting only one. We were rolling only one. Now we are rolling two. sided dice. What is the probability of obtaining number 7? So one idea that some people can have is like this, yeah? That this is the sample space. These are all the possible outcomes. You can obtain number 2, number 3, number 4, 5, until 12. This is in the case when you obtain 1 and 1. Yeah? This is the smallest number that you can obtain. You can obtain 1, for example. And the highest number that you can obtain is 12. So if you do that, as a sample space, you cannot use the classical approach, because the classical approach say that you can use it when all the events have the same are equally likely. And I think 2 is not equally likely to 6, because 6 can be obtained in different ways. You can obtain 3, 3, 4, 2, for example, 2, 4, or 5 and 1. So there are many ways to obtain 6, or several ways to obtain 6, but there is only one way to obtain 2. So for that reason, since these outcomes are not equally likely, this is a wrong set to choose as a sample space, yeah, in the classical approach. So look at this, this is a wrong idea. This is definitely a wrong idea. If you are going to use a classical approach, you need to find as a sample space one, or you need to see this as you need to see the problem as a sample space when each outcome are equally likely, have the same probability. And this is if you do this, yeah. For example, you use the sample. A very good sample space will be like this. It will be that all the outcomes that have the same probability or that are equally likely are this. For example, you can obtain 1, 1, 1 in the first die and one in the second die. Let's say, or you can obtain 1 and 2, for example, or you can obtain 1 and 3, or 1 and 4, and each of these outcomes have the same probability. They are equally likely. So this is only 1, 1. There is only 1, 2, 1, 1, 2. There is only 1, 1, 3. All of them are equally likely. 1, 5. All the outcomes whose first die in the first die you obtain number 1, and finally 1, 6. But of course, you can obtain 2 in the first die. Yeah? So 2, 1 will be another possible outcome, or 2, 2, or 2, 3. Or all the outcomes when 2 is the first outcome, or the outcome in the first die. 2, 4, 2, 5, 2, 6. Or what happens if the first die have 3? Yeah, 3, 1, 3, 2 until 3, 6. Or if in the first die you obtain 4, all these 6 outcomes. Or if in the first die you obtain 5, or if in the first die you obtain 6. So in total, these are the total possible outcomes. There are in total 6 times 6 equal 32 outcomes. Sorry, 36 outcomes. So the number of elements, and now they're asking me what is the probability of obtaining 7. So now, as the event, I'm going to see what are the favorable outcomes. So what are the outcomes when you obtain 7? If you obtain 7, if you get 1, 6, or 6, 1, for example. So one possible outcome for the events will be 6, 1. Yeah? Another will be 5, 2. Yeah? So you obtain 5 in the first and 2 in the second. Or maybe 4, 3. Or maybe 3, 4. Or 2, 5. Or 1, 6. 1, 6. And that gives me all the possible outcomes when you obtain number 7. Let's close this bracket, and then we can compute the probability. The probability of E will be the number of elements in E, that are 6, divided by the total elements, the total number of outcomes, 36. And this is 1 over 6. You can type it in decimal. I type it here with 4 decimal, an approximation to 4 decimal. And or you can type it as a percent, 16.67%. That concludes the examples for the classical approach of probability. But this is not the only way to define probability. Let's see this situation, and this is what we call the empirical approach. I'm going to explain this with an example. Imagine that we have this. What is the probability of obtaining a head when tossing a biased coin if, when it is tossed 400 times, 98 heads are obtained? So you see here, if we have a coin, the usual situation is there are two outcomes, and these two outcomes are equally likely. And this is what that happens when we have a fair coin. But this coin is not fair. If there is a if this coin is heavier in one of this of the side, maybe the head and tail are not equally likely. And it looks like this is happening here. You toss this coin 400 times and you obtain only 98 heads. What is the probability of obtaining a head? So if you have this, a good idea is to use the relative frequency as a probability. And this is what we call the empirical approach. So the empirical approach defines the probability as the relative frequency. So the number of times you obtain, so you make the experiment, and the number of time you obtain the event, the number of times this event happens, divided by the number of times, the total number of times that you make the experiment. So we call this the sample size. So let's say this, we are going to write it in this way. Number of times the event occurs, divided by the total number of observations. In this case, you make in total 400 times observations, and you see that that happens 98 times. So we have that this is the relative frequency. Remember one of our first videos, yeah? So the frequency divided by n. So it will be 98 divided by 400. So this is the relative frequency. And this is 98 divided by 400. I obtain 0.2450 or 24.50%. So whatever example like this, when you really need to make the experiment because you notice that they are not equally likely the outcomes, then you can use the empirical approach. And if you notice, the empirical approach also follows the three properties of a probability. So it will be always a number between 0 and 1. The probability of the whole sample space, so the probability of everything that happens, it will be 400 divided by 400. It will be 400 divided by 400 is 1. Yeah. Or the probability of nothing happening will be 0 divided by 400 will be 0. So it satisfies all the three properties of the probability. Let's see another example. Listed in the table is a frequency distribution showing the advertising expenditures for some manufacturing companies. What is the probability that the company expenditure is between 55 to under 65 millions? And this is the table. So here we have that there are 5 companies that spend in advertising between 25 and 35 millions, and there are other things that spend between 35 and 45 millions, etc. And they're asking me what is the probability that the company expenditure is between 55 and 65, and somebody makes the experiment. So we are going to use the empirical approach. Yeah? And then because somebody made the experiment, I'm gonna use the relative frequency to compute the probability. So this is the probability that the expenditure is between 55 and 65, and between 55 and 65 we have 16 companies. In total, the observation that we made were 60. So we have that the probability of this event will be 16 divided by 60. Yeah? 16 divided by 60, and what I obtained in decimal was 0.2667. that is equal to 26.67%. And that's the way that you compute the probability in an empirical using the empirical approach. Later in other videos I will be showing how to compute probabilities in other ways.